Google's AI finally detected what we all suspected about Apollo moon missions. A groundbreaking AI analysis is rewriting everything we thought we knew about humanity's first moon landings. Has machine intelligence decoded the biggest puzzle of the moon landings? For decades, whispers insisted we never left the Earth. Grainy footage, shadows at odd angles, the flags that seemed to move, each became a lodestone for doubt. Now imagine pointing modern large-scale artificial intelligence at the entire Apollo record. Video frames, audio, transcripts, telemetry, photographs, even independent observations would be analyzed. Then one ruthless question arises: does it hang together? The result would not be a meme or a hunch. Instead, it would be a probabilistic audit that either collapses a myth or a conspiracy. This feature is a speculative science-backed thought experiment. It asks what a state-of-the-art AI system would find if it re-examined Apollo from first principles. Moreover, it considers how those findings compare with physical evidence on the moon and in Earth-based measurements. A spoiler: there's a lot more to test than a famous footprint. Along the way, we'll reference publicly available high-authority material. You can check primary timelines, hardware, and mission context via historic mission reports, media coverage, archival mission timelines, encyclopedic overviews, and a comprehensive mission summary. What exactly would Google-grade AI do? Google's AI is a shorthand here for a modern production-scale stack. It includes foundation models for vision, audio, text, and time series data paired with image forensic and geospatial pipelines. Think of it as 4 overlapping audits. 1. Visual forensics, image and video. Deep models are trained to spot comprehension anomalies, lighting inconsistencies, resampling seams, and synthetic content cues. Peer-reviewed surveys show that deep learning detectors now outperform many classical forensic algorithms. 2. Photogrammetry and physics. Geometry-aware AIs can reconstruct 3D scenes from multiple frames. They estimate sun position, shadow vectors, camera intrinsics, and surface normals. And then they test whether footprints, horizon curvature, and object scales match a low-gravity, airless body. 3. Telemetry and time series alignment. Sequence models match audio callouts, biomedical sensors, and spacecraft telemetry to external phenomena. These include engine gimbals during burns, antenna handovers, or Doppler shifts. If anything is fabricated, misalignments often appear in timing, phase, or noise statistics. 4. Cross-source consistency. NLP language models ingest transcripts, checklists, and post-mission reports. Then they cross-reference them with archival events and independent observations. Contradictions get flagged for human review. It's not about trusting AI. Instead, it pressures the data against the laws of optics, mechanics, and probability. Additionally, it checks against independent measurements taken long after 1969. The first stress test: lighting, shadows, and lenses. A persistent claim says lighting looks studio-like. A geometry-aware pipeline would recover sun azimuth and elevation from shadow directions on multiple objects. Compare observed brightness fall-off with an airless environment where no atmospheric scattering fills shadows. Model and camera lens flare and film response. Apollo cameras use specific film stocks, apertures, and exposure sequences. These produced characteristic halation and grain. When such reconstructions are applied to Apollo imagery, the expected signatures of harsh collimated sunlight and an airless high-contrast surface appear. This is exactly the regime reported in the historic mission report and the encyclopedic overview. Moreover, the patterns match modern orbital images of the same terrain. Algorithms can thus cross-check rock placements and gentle slopes around the landing site. The second stress test: boots on the ground from orbit. One of the cleanest tests needs no Earth studio, no film tricks, and no memory. Simply look down from lunar orbit today. NASA's Lunar Reconnaissance Orbiter, LRO, has imaged the Apollo 11 site at meter-scale resolution. That's how specific it can be. You can see the lunar module descent stage and the trails between experiments. Additionally, independent spacecraft have weighed in. India's Chandrayaan-2 orbiter imaged Tranquility Base and resolved the Apollo 11 descent stage from a completely different camera and trajectory. Conspiracies must then explain not one but multiple spacecraft, nations, instruments, and teams aligning on the same hardware still sitting at the site. A modern vision model comparing ground photos to orbital shots can confirm that boulder fields, craterlets, and traverse arcs line up within photographic tolerances. Therefore, any large-scale fabrication must replicate the moon's surface as seen from space across multiple years and countries, a formidable bar. A third stress test: laser retroreflectors still blinking back. If AI had to choose a single decisive external datum, it might pick this laser ranging. Apollo crews placed mirrored retroreflector arrays on the surface. Decades later, observations on Earth still dual-fire laser pulses at the Moon. They measure the return time off those reflectors to millimeter precision. This tracks Earth-Moon distance, lunar vibrations, and even tests aspects of general relativity. Consequently, an AI auditor does not need to believe a photo if the mirrors keep answering back. The fourth stress test: timeline coherence. Deep language models excel at alignment across sources. Feed them the launch time, translunar injection, landing timestamp, and EVA durations. Then validate these numbers against radio tracking and the archival mission timeline. Apollo 11's landmark moments: 2011 UTC landing on July 20, 1969, first steps at 2:56 and 15 seconds Universal Time coordinated on July 21, splashdown on July 24, are precisely documented. They are observed worldwide and corroborated by independent tracking stations and competing nations' astronomers. AI's job here is bookkeeping at scale. It looks for impossible overlaps. For example, telemetry calling a burn that the dynamics don't show. However, what it tends to find instead is consistent noise, the kind you only get from real-time human operations under stress. Could AI still find anomalies? Almost certainly, because anomalies are normal at the edges of human endeavor. Expect oddities in audio compression, missing film frames, or variations in exposure. These reflect hurried adjustments under novel lighting. An anomaly detector flags these. Then a physics-aware model tests whether a mundane cause explains a pattern. Examples include signal dropouts, magazine swaps, or film jamming. For example, models might notice that some shadow edges look blurred in certain shots and sharper in others. In an atmosphere, this would be suspicious. On the Moon, however, the culprit is often grain, exposure, latitude, and the surface microtexture. Additionally, the Sun's low elevation and small undulations create steep local contrast changes. Multi-frame photogrammetry and orbital crosschecks turn looks weird into matches terrain. And what about classic claims? Why are there no stars? Short exposures were set for a sunlit surface. Stars are too dim to register. A vision model can simulate the camera's exposure and show that star fields would fall below threshold. The flag moves, there's no air to flutter. The horizontal bar holds it open. Any motion occurs when the pole is twisted or when the fabric oscillates briefly in low gravity. This behavior is precisely modeled by a dynamic engine with lunar parameters. Shadows look inconsistent? Uneven terrain and wide-angle lenses cause converging shadows. Photogrammetry reproduces this when you use the correct camera intrinsics. Again, AI cannot perform eyeballing images. If it happened, we should see it now. We do. Multiple orbiters have imaged hardware and tracks. Lasers ping retroreflectors. Third-party observatories still get returns decades on. A tougher test: adversarial thinking. Let's Steelman the hoax. Suppose an AI found local inconsistencies in a handful of frames. Say a suspicious edge profile or an interpolation artifact around the helmet reflection. And what then? First, AI would check adjacent frames from the same row. This rules out scanning or digitization artifacts introduced decades later. Second, it would triangulate against independent sources, TV broadcast tapes, kinescope stills, and separately recorded audio that ground stations archived. Third, it would test the hypothesis. If a scene were staged indoors, lighting would produce certain multi-shadow signatures or specular profiles that must repeat across angles. Do they? Generally no. And they conflict with orbital terrain seen later. In other words, small anomalies rarely scale into a consistent alternative world. Large conspiracies must paradoxically fit more data than reality itself. Why modern AI actually reduces uncertainty? Early debunking relied on expert explanation. Today, explainers are reproducible code. An open pipeline can ingest public Apollo data, rerun the photogrammetry, and spit out 3D scenes. Any researcher can interrogate them. Detectors for synthetic imagery and splicing are advancing rapidly. They catch diffusion model fingerprints and resampling traces. This progress does not merely police today's deepfakes. It retroactively hardens confidence in legacy footage when it passes modern tests. Additionally, the Moon itself acts as a silent external hard drive storing tracks, hardware, and optical retroreflectors. These cannot be forged from Earth. Where speculation is warranted, there's a better question to ask AI than, was it faked? Try this: surface science at scale. Train models on every frame of regolith interaction. Dust plumes, boot compressions, rover wheel slip, to refine granular physics under vacuum. Human factors under cognitive load. Analyze speech patterns to study stress, decision-making and teamwork in extreme environments. Lessons aim at future crews on the lunar South Pole and Mars. Hardware aging. Use orbital images to model thermal cycling and micrometeoroid wear on decades-old artifacts at the Apollo sites. This predicts survivability of future base infrastructure. These are the kinds of surprising findings an honest AI audit should deliver. New science from old data. And moreover, they complement the coherent story preserved in the 5 approved links. So, did we witness history or was this a huge illusion? A rigorous Google-scale audit would not just glance at a few photographs. It would fuse vision, physics, language and independent measurements gathered over half a century. On those grounds, the Apollo record does not crumble. Instead, it overconstrains the truth. Orbital cameras from multiple nations show hardware and tracks exactly where they should be. Laser retroreflectors still answer from Tranquility Base and other sites. They return photons across 384,000 kilometers with timing that refines our models of gravity and lunar motion. Timelines, transcripts, and telemetry interlock to the second. They match external radio tracking and documented procedures. If there's a small inconsistency in an old photo, it does not outweigh decades of corroborating data. Modern AI would flag it, model explanations, and integrate it with external evidence. And as a result, it ultimately strengthens the historical record. So for decades, Apollo conspiracies thrived on anecdotal oddities. Today, a multimodal AI audit can stress test every element: lighting, shadows, physics, telemetry, orbital verification, and long-lived retroreflectors. The result: a consistent cross-validation record that withstands scrutiny at scales humans could never achieve alone. This is one collective spark. Please leave your comments and thank you for your support. Please support my Patreon account. The daily posts are 5 videos daily and they are totally different from what I have on my YouTube channel. Thank you so much for your support and that you find all my content so interesting. You'll find the Patreon account details in the description box below.